Mm. Hello everyone and welcome to Geotechnical webinar. My name is Seung-Wan and I will be delivering this presentation for you. Today I will talk you through overall process of soft ground design, especially focusing on 1D consolidation analysis method. Okay, before we start, let me first give you a brief overview of using GoToWebinar. I know everyone can hear me. And in terms of the screen, if you want to maximize the view, just click on the two hovering boxes in the top right hand corner. If your screensaver comes up, you can simply wiggle the mouse from time to time or just set it to off. Okay, a few other things to know. If you want to minimize the window, you can use the left arrow for that. If you have any question, you can use the chat box for this. We have a technical support engineers on standby to answer questions right away. Or if we cannot cover some of the questions on the spot, we will make sure to answer them via email after this session. Before we start this session, let's check quickly what Okay, this is SoilWorks, which can handle all kinds of geotechnical issues such as ground excavation, slope stability, soft ground, seepage, foundation, and dynamic, like evaluating seismic capability. Today, for the first session, I will focus on the analysis and design of soft ground with several case studies. We are going to start with definition, and I will talk about the crucial points that must be considered when you perform 1D consolidation analysis. And we'll go on to the design process of soft ground, and then we'll demonstrate several case studies such as how to get critical height of embankment and optimum drain spacing automatically, and conclusions. First of all, definitions. What is soft ground? Soft ground is very compressible deposits such as clay, silty clay, clay silt. Because these kinds of deposits have a very low permeability, water level is generally located on the ground surface. And if constructing the embankment over the soft ground or excavating some area, it can result in loss of settlement or failure of the ground. But these days we have to construct embankment over the soft ground due to the lack of suitable land for infrastructure and other developments. So we have to make a decision for optimized improvement method, and this is why we get together today. Okay, soft ground is weak, but in terms of strength and compressibility, those are relative to the magnitude of the applied loading and structure that is supported. Among many reference and literature, Terjagi and Peck have proposed the following classification of clay based on the SPT, Standard Penetration Test, and CPT test result. So when we carry out an embankment design and selection of the most appropriate construction method for soft ground, we must consider these issues: initial and long-term settlement during and after construction, and tolerance on settlement and differential settlement of the proposed developments or structures, and heaving or boiling during excavation and lateral ground floor are also many concerned issues when it comes to dealing with designing soft ground. So when we select the most suitable soft ground improvement, we have to fully investigate the site condition in terms of geological and geotechnical parameters. Okay, following table is the improvement method according to the improvement objectives and application. The respective features of this method can be used as reference in selecting suitable ground improvement. We might consider modifying the embankment geometry. For example, if we reduce the slope angle or construct the counterweight berms, it will result in improvement of the embankment stability because of increasing the length of failure surface in the soft ground. But this method is required for more length take and volume of wear. So in terms of cost effectiveness, we need to compare with possible alternative methods like this table according to the improvement objectives. Excavation and replacement of soft ground can provide more strong and less compressible foundation or drainage to accelerate consolidation. Sometimes you can implement like EPS block to reduce applied load. In order to increase the bearing capacity, we can apply geosynthetic or stone column. Okay, let's move to analytical overview. There are three main concerned issues when analyzing the soft ground. That is settlement and calculation and degree of consolidation and increase in strength of soft ground. Okay, so consolidation analysis is associated with drained, undrained analysis, and it is to calculate the process of dissipation of excess pour pressure. The excess pour pressure takes place in case that the water resists external loading, so the reduction in excess pour pressure with time can result in the increase in effective stress. During this process, the soil particles will be close to each other and accumulated over time, meaning that the soil will experience the settlement in the direction of gravity. So consolidation analysis is largely classified into theoretical one-dimensional consolidation analysis method and the finite element method. There are pros and cons. One-dimensional consolidation analysis enables the user to easily obtain the result through a simple process. And otherwise, the finite element analysis method can be more applicable in a generalized or complex ground analysis, but the modeling and analysis may take a long time. The thing is, SoilWorks support both analysis methods. In this session, we will focus on the 1D consolidation analysis because it is more effective and save time and cost and applicable to get design parameter in practice. Okay, so first, the settlement of soft ground caused by applied load can be divided into three stages. Let's say initial settlement, primary consolidation, and secondary compression. First of all, initial settlement. In case of sand, settlement takes place immediately after loading. The settlement of sand can be calculated with these kinds of simple equation. In SoilWorks, the Debye and BK graph method, as you can see in this slide, are used with SPT values. The excess pore pressure dissipates with time and the clay undergoes further settlement due to volume changes. The rate of volume changes and corresponding settlement is governed by how fast the water can drain out of the clay under the applied loading. So one-dimensional primary consolidation settlement can be estimated using these oedometer consolidation tests and equations. And SoilWorks provide the following three methods to calculate primary consolidation. Clay can be classified by stress history, that is normally consolidated, under consolidated, and over consolidated clay. This MV method can result in large errors in the over consolidated domain, and since E0 E0 method depends on the variation of test data, is not commonly used in practice. In general, the CC method is most commonly used for all kinds of clay, but the other two methods can sometimes be more applicable according to the site condition and type of data you got from the test. Next one is the rebound of cohesive soil. When the embankment or external load is removed, cohesive soil will rebound, and the rebound calculation according to different settlement calculation methods are as follows in this screen. For different calculation methods, the removal factor can be estimated from slope of E log P curve after removing load. The removal factor is always considered to retain the positive sign. And if the removal factor is 0, it is assumed that no rebound takes place upon unloading. In case of sand, the rebound does not occur. And secondary consolidation. Even after complete dissipation of the excess pore pressure and the effective stress are about constant, there will generally be further volume changes and increased settlement. It is called secondary compression. In general, we need to assume the total secondary consolidation time, sometimes it's a couple of decades, so that it is difficult to estimate the amount of secondary consolidation precisely by theory itself. If this consolidation seems to be critical, we can usually consider solidification method, excavating and replacement of soft ground. Some engineers used to exclude this from the total settlement. Actually, there is no right or wrong answers, so it depends on the site condition, the importance of adjacent structure, and engineering mind. The SoilWorks calculate the primary and secondary settlement separately, and then you can select the primary or both for the total settlement. Okay, let's go on to the rate of consolidation and degree of consolidation. The calculation of the consolidation time is based on the Terzaghi one-dimensional consolidation theory. So this CV, this is coefficient of consolidation, and T is consolidation time, and HD is drainage distance, single or double. So we can define the time factor by the Terzaghi simple equation, and also we can get the degree of consolidation according to the time vector with this equation. The final issue of 1D consolidation analysis is the calculation of increase in strength of soft clay. The strength increase ratio due to the applied loading is given by following empirical equation. There are simple methods can estimate using plastic index or liquid limit, but the result from triaxial compression test will be more reliable. If it is hard to take some tests due to the site or work condition, I think you can take one from following table. It is generally ranges from 0.5 to 0.5. Okay, if so, why we have to get the value of increase in strength of soft ground? That is to estimate the stability of the embankment with taking account it. The stability of the embankment is commonly assessed using a limit equilibrium analysis. So SoilWorks provide the following 6 analysis method. The other one excluded in this table is the Felenius method. It is a very old and conservative one, which neglect the horizontal force from equilibrium equation. And I do not want to recommend to use the other simplified method like Bishop and Yambu, regardless of reducing in computing time. This method can be shown inaccurate, over or underestimate the result against the horizontal force and cannot consider the moment equilibrium. So I recommend to use method like Spencer or Morgenstern Price and Salma, especially for Rockstrom. Okay, let's go on to more practical issues. Following is the design process of soft ground. First of all, we have to check the design criteria such as total construction period, final level of embankment, and allowable residual settlement. And we have to investigate the site condition to get these kinds of analysis and design parameters. And we will compare various alternative improvement methods in terms of consolidation and embankment stability. And then we will be able to make a decision what is optimum improvement method for this site. During this process, what is the most critical and influential factor for design? Finding the best compromise between cost effectiveness and stability. This is a kind of destiny of engineers. So we need to evaluate both the magnitude and rate of settlement of the subsoil so that the settlement in the long term will not influence the serviceability of the embankment. In carrying out the stability analysis, an iterative process is required in the estimation of settlement because the extra field required to compensate for settlement will lead to further settlement. During this process, SoilWorks can be used to make a decision for this step. And today we will experience all of steps with SoilWorks. Preliminary analysis can entirely substitute for Excel. And we have parametric analysis to get drain spacing and preloading height. And we can perform slope stability analysis taking account increase in strength of soft ground. And all results will be consolidated in one report generated automatically after analysis. Alright, now we will take a closer look at the most significant part of soft ground design through several case studies. This is a plan drawing of soft ground based on the site investigation and the construction plan, like structures or road. In this plan drawing, each section has different ground conditions, including its depth and final level of embankment based on the construction plan. In this case, we had to analyze and design for the total 32 sections. So can you imagine that how many times we have to repeat trial and error to get more reasonable value for design? In general, engineer has to run analysis more than 5 times for each section to make a decision the most appropriate and applicable improvement method. Okay, so first case study is the preliminary analysis. We can estimate the total settlement and rate of settlement, degree of consolidation, only with these kinds of geological and geotechnical information, only with this information. And then we can make a decision whether this section is needed to be constructed, any kinds of improvement method or not. So for this project, the total 50 cases had been performed with different layer thickness and ground properties. In preliminary analysis, we can define additional factors like landfill thickness between embankment and soft ground and the position of water level. Okay, this is the dialogue for preliminary analysis. So after analysis, just input the value you want in terms of geometry and material property. So after analysis, we can get following result for each case: the total settlement, rate of settlement, and residual settlement at the end of improvement period. In general, the allowable residual settlement according to the weak layer thickness is as following table. So based on the target construction period, let's say 2 years, 30 days, and design criteria like allowable residual settlement, let's say 10 centimeters, we can make a decision which section having what kinds of profile are needed to be constructed improvement method. For example, if the final level of the embankment is 3 meters, this red curve, and if the thickness of soft ground is less than 6 meters, the section having this profile will always be within the allowable range even without improvement method. So using this result, we will be able to reduce the total analyzing time for the all of section drastically. Okay, after preliminary analysis, we can classify which section needs to be detailed analysis. Like this section, which the residual settlement within 2 years exceed allowable one, we need to apply preloading to reduce the residual settlement and drainage to accelerate the consolidation. Even though the engineer has a lot of experience for design this kind of case, in order to find optimized drain spacing and preloading height and the critical height of embankment, the engineer needs to check more than 3 to 5 times at least. Drainage method and preloading height. Okay, so in order to get design parameters for this kind of section, iterative analysis is required. So in SoilWorks, we can get all results for each analysis at once through parametric study. And all results are summarized into one graph and table automatically. Moreover, after consolidation analysis, you can create slope model with considering the strength increase of soft ground, so can check the slope stability as well. I will go on to explain modeling and analysis and design procedure for each case. First, in order to make geometry of section, you can just copy from AutoCAD and paste to SoilWorks model view. Or you can draw the geometry directly on SoilWorks model view using CAD-based functions. And next, smart surface. SoilWorks will find the cross domain and then make surface for each domain automatically with just one click. And then you can assign the material property to each surface with just drag and drop. Drag the material property from worktree and drop the model view after selecting designated surface. The next step is to define the settlement calculation position. In general, we set the position at an interval of about 5 meters from the position that the maximum load is applied. You can create the calculation position automatically with the distance increment and the number of positions. In order to set water level, you can select the existing line, or you can draw additional polyline and select it as a water level. And then you can create various analysis cases with one models. For example, you can make a single stage analysis or multi-stage analysis after defining construction stage, and you can include or exclude the drainage in the analysis case. So after performing analysis for all cases, all results can be shown in one chart or table, and you can generate a report automatically. It includes result analysis and summary table, so you can figure out critical design parameters very easily. Okay, now we are going to take a close look at the second case study. This is to design the minimum preloading height, let's say critical height of embankment. The embankment over soft ground will result in settlement of ground, so in order to remain the final level of embankment, it is essential to apply additional embankment as the amount of settlement. And if there are some live load like traffic load on the embankment, we have to apply preload to guarantee the stability against the additional settlement after construction. So for this case, we have to calculate the optimum preloading height before construction. The main purpose is to minimize the amount of removal soil after getting target degree of consolidation, meaning that the residual settlement is within the allowable range. So in SoilWorks, we can check the total and residual settlement for each preloading height at once automatically. In preloading parametric analysis dialog, you can select the surface you want to apply preload and then define height increase and the number of increment. After then, analysis case will be created automatically. In this case, in order to get optimum preloading height, I set the total 2 meters of preloading at an interval of 20 centimeter increment. So after performing analysis, we can find all results in one chart or graph in the post dialog like this. So we can figure out easily the minimum preloading height based on the design criteria. And you can export this result to Excel as well. Okay, let's look at the result analysis in detail. This is the table in the report generated automatically after analysis. For this case, the target improvement period was 2 years 30 days. And as in the above table, the residual settlement exceeds the allowable one. This means we need to apply preloading to reduce the residual settlement. As below table, we can figure out the target degree of consolidation is about 90% when the residual settlement is close to allowable one. After that, we can check the residual settlement for each increment of preloading height as table above. We might make a decision that the minimum preloading height is 0.2 meters based on the allowable residual settlement. Because it is less than 0.1 meter, however, the occurred settlement exceeds the preloading height, so we can figure out it is required to apply more than about 1 meter to compensate for settlement in this case. So if you increase the preloading height by 1 meters, the occurred settlement also increase, but it is very close to preloading height and the residual settlement is within the allowable range as well. So from this result analysis, we can make a decision the optimum preloading height as 1 meter easily. Actually, 20 of increment is too rough estimation. Even a couple of centimeters of embankment costs a lot. So if you use Excel or the other software, equivalent software for this analysis, you will have to perform the same process, repeat again and again, more than 10 times to get these values. Next, this is to get the maximum drainage spacing. This improvement method is to accelerate consolidation. Even though you get the minimum preloading height as previous slide, the duration to achieve this residual settlement is much more than the target construction period. This is why we need to accelerate consolidation with drainage like PVD or SCP. In this case, PVD is applied for this area. This method is only for accelerating consolidation. Otherwise, SCP, sand compaction pile, is applied to this area. It is not only to accelerate consolidation, but reinforcement of bearing capacity to resist against the slope barrier. The purpose of this parametric analysis is to get the maximum drain spacing, so can minimize the cost of construction. Therefore, we need to compare all results with different spacing based on the allowable residual settlement. Okay, in SoilWorks, we can check the total and residual settlement for each drain spacing at once. In drain spacing parametric analysis dialog, in this dialog, you can select the surface you want to apply drainage and then define drain spacing you want to check. After then, the analysis case will be created automatically. In this case, in order to get optimum drain spacing, I set 5 cases at an interval of 20 centimeters. Okay, after performing analysis, just like preloading analysis, you can find all results in one chart or graph in the first dialog like this. So, okay, let's look at the result analysis in detail. For this case, the target improvement period was 2 years, 730 days, and as in the above table, the residual settlement exceeds the allowable one. After running parametric analysis, we can get below table, so can figure out which spacing has a residual sediment within allowable range. In this case, 0.9 and 1.1 meters satisfy the design criteria, so we can make a decision 1.1 meter is more suitable in terms of cost effectiveness. In case of SCP, we can follow the same procedure. Three kinds of spacing satisfy the design criteria simultaneously, so we will select 2 meters of spacing for the same region. But in this case, we have to pay attention for final decision. It means we have to make sure of slope stability simultaneously for this area. If the factor of safety after coupled analysis is less than the design criteria, like let's say 1.2 or 1.3, we have to take smaller spacing or increase the substitution ratio of SCP. So this case study is for coupled analysis. The stability analysis must be performed both short-term and long-term. It means that we need to check the stability right after construction before account of any increase in strength, and long-term stability after account of increase in shear strength of soft ground. So in SoilWorks, we can check the stability before and after account of increase in strength with slope models generated automatically. Let me show the procedure of coupled analysis. After running 1D consolidation analysis, we can check the increase in soil strength by stage in the post dialog, like this. And PBD area, the cohesion will increase with time, but right after casting, the cohesion will decrease due to the ground disturbance. In case of surface installed SCP, the friction angle will increase because of the concentration of stress on the sand piles. The reduction in stresses in the cohesive soil result in increase in the bearing capacity. If the 1D consolidation analysis is complete, every complete analysis case can generate a slope model. So select create slope model, and slope model files before and after the strength increase automatically generated in the folder where the consolidation model is saved here. The slope model files are named after the analysis case name. In the case of construction stage analysis, the slope model files are generated for each stage. For example, if there are 3 construction stages, 1 is the model before the strength increase, and number 2 is the model after strength increase due to the first filling. In the same manner, 3 the last is the final slope model where the strength increase is applied after construction is complete. And then if you open automatically generated slope models, you can check the number of material property as the number of surface you model. And each material property is already assigned to the designated surface. After then, you can check the slope stability by limit equilibrium method like this for each stage, before and after account increase in soil strength. If the factor of safety is less than design criteria you apply, you can back to consolidation analysis and change SCP substitution ratio or spacing to ensure slope stability. Next, I would like to present another case study it is to estimate the maximum critical height of embankment without slope failure. In order to fill soil on the soft ground by the final level of embankment, we need to make a decision between single-stage and multi-stage construction. If we can fill all of soil at once without any failure, it will be the best. But in the real world, almost critical cases have been doing with multi-stage construction. So multi-stage loading is allowed to increase in strength as consolidation, but the rate of filling must be limited so that the ratio of load is within the acceptable factor of safety. In this case, the iterative process is required. So first of all, we need to perform 1D consolidation analysis with a single stage and then create slope model. In the slope model of the model before increase in strength of soil, we can divide the embankment surface horizontally at an interval you want automatically. After then, we can execute slope stability analysis for each stage, as you can see in this video. So we can compare the analyzed factor of safety with the design criteria, say 1.2 or 1.3. The less failure criteria is more conservative. From this result, we can make a decision the critical height for first stage at the moment right before the factor of safety is less than the criteria. After that, we can back to consolidation modules and performing 1D consolidation analysis with multi-stage. For the second critical height of embankment, we have to open the model after increase in strength of soil by first filling. And then we can follow the same procedure as you can see in this video. Through this process, we can define the construction stage, the critical height of each stage with guarantee of slope stability. Finally, I want to let you know about the importance of model geometry. As you can see, these two models have the same geometry, and only difference is the area of each surface of soft ground here. Area of each surface. What if you take the same time to model 1 and 2? Which one you take to perform consolidation and coupled analysis? In case of number 1 models, the area of soft ground is classified very well according to the geometry and material of embankment, slope, load, sand, concrete. But in this case, this area has the same increase in strength like cohesion and friction angle. So we need to take a closer look at. Do you think it is reasonable that this whole area has the same increase in strength? In the real world, soft ground will experience different magnitude of loading by each position. Number 1 model is good, but we need to take account increase in strength as detailed as possible to get the design parameters more close to real world. So in SoilWorks, with smart surface function, either take the same time to model, no matter how many times you divide the surface. The smart surface function is not just a convenient one, but the functions that can make the impossible models possible for 1D consolidation analysis. Okay, let me conclude for the first session. The requirement for a successful construction of embankment over soft ground can be summarized as follows. First of all, we have to set the design criteria in terms of allowable residual sediment and factor of safety against the slope area. And cost. Cost is much more important, including and construction and maintenance cost and construction period. Secondly, we should well know about geological and geotechnical information through site investigation and lab test. This will take effect on the analysis result and design parameters directly. Third, design process. This is also related to the cost effectiveness, how much time it's going to take to get applicable throughable design parameters, which can ensure both stability and deformation. Finally, monitoring during and after construction. Nobody can predict exactly what's going on during and after construction. Sometimes we need to take a back analysis with more appropriate design parameters during construction, or have to design the additional reinforcement method after construction. Okay, finally, I would like to talk about the vision of SoilWorks. SoilWorks had released at the end of 2010 in Korea. And from April 2011, we have begun to export all SoilWorks to other countries like Japan, China, and America. Especially Japan, SoilWorks has captured more than 90% of seismic design market. And we already released SoilWorks to Russia, Spain, Italy, Taiwan as well. So we will be able to implement design criteria of these countries, and you can also experience through our program. I want to say SoilWorks is not a just program, but a geotechnical engineering solution partner. This is why we have developed SoilWorks. So I can assure that SoilWorks will be able to the best partner for you. Thank you for your attention to this session. And I hope this will prove useful for your ongoing and prospective project. So if you have any question, you can send me email on this screen, and all technical material you can download from our website. And if you want, if you send an email, I will send you the model file. This is the all model file for this case study from drain spacing and preliminary analysis and preloading. You can ask through email, and I will send you all final models and this presentation file as well. So thanks again, and have a good day, and hopefully see you in the next geotechnical webinar. Thank you. Bye bye.